So, work energy problem, I think.
Way back when?
Oh, way back when. Yeah. But there's a test coming up next week.
Freaked me out.
And so, wait a minute, I haven't seen this in a while. So, this part here is what? This part of the problem is projectile, which we learned in chapter 12. You were exposed to it. Whether you learned it or not is a different question. And what does it depend on? In the x direction, right, x is equal to v0 t. Right, in the y direction, you get y final is equal to y initial plus v0 yt, which is 0, minus 1/2 gt squared. And so this doesn't change, and this doesn't change. And so the time is always the same. The time to fall is independent of your initial velocity. And so therefore it's the ratio of the velocities is the ratio of how far you need to do that. How do you find your initial velocity? It's a spring work energy, so we have 1/2 k x1 squared equals 1/2 m v squared. And so you have an x1, you have a certain velocity, so you need to figure out what the x2 is to get the proper initial velocity, how far you back. That's basically how you go about this problem.
So you solve for your b, plug the g into your x, and you solve for your t with y. Plug that in. So you got two separate things.
Well, it's just a ratio of the velocities. How far you go is just a ratio of this distance to d is your relationship of your initial velocities. And then basically initial velocities, you can get your initial x's. And since it's squared, it works out. You're given x1, you're trying to find x2.
You're not giving any numbers.
But you're not giving it any numbers. And so it's basically ratios. All right. What time's Monday? Monday doesn't work.
What?
So for review, because I've got class all day Monday. I've got senior design on Monday. So do we have labs the afternoon on Tuesday, or Tuesday good?
It's canceled though. Our thermal lab's canceled.
Oh yeah, soil stuff.
Yeah, we have
Oh,
soil.
yeah.
What? Well, that's can't.
We could do that single after lab.
No,
That's not.
I've got a family.
I got a family.
Our lab's at 4 and then 3 to 4 is like.
So 3 to 4 works?
Yeah.
Tuesday?
Yeah.
I'm gonna see.
It works.
Do we have more? You guys free in the morning at all, or no?
No. I'm not free until 1:30.
8? No. So we got 10 to 11, 11 to 12, 12 to 1. All right. Flicker time.
This is Tuesday. Maybe she should just show up on this.
Are we finished with that?
What are people missing?
So this is Tuesday, because I can't do Monday. Monday.
How are we going to do this? First,
There's more than E.
Oh, first we
we
need
do
to
it in halves.
Okay, we're doing okay. No, we don't need to warn this.
Just do the first four.
All right, so the first one, 10 to 11.
What is which?
Oh, good question. A is yes, B
It's
is
just whether or not you're available.
whether or not you're available.
No.
All right, this is looking pretty
Obvious.
obvious. Okay, let's just stop this. B is the correct answer. How about 11 to 12? Is that everybody? All right, someone is, all right. 12 to 1. One more person? All right, 1 to 2. I guess this should be a half-hour increment, it's not. All right, 2 to 3. That's 19. 3 to 4. Okay, start. Ooh, that looks good. So it looks like 3 to 4 is the time. All right, 4 to 5. Five to 6. Disruptive class.
I need a clicker.
All right.
I'm not even registered for the class. It doesn't matter.
No?
What time?
C. 5 to 6. All right. So it looks like 2 to 4 is the 3 to 4 is the time that most people can make it. If you are one of the 2 people who can't make it, you can give me some other time. I will post. If we go over the test solutions, and I'll post the solutions online for those who can't make it. What? We're going to the homework, could be another option. So I will answer questions that you have. So we've already checked the homework. Reading quiz is next up. Disc rolling on a surface without slipping. The acceleration of the center of gravity will be something, and the friction force will be something. What are those special?
I'm so fast.
All right, 25 seconds total. You've already missed this. All right, that's everybody. So apparently a C is the right answer. So whenever you're rolling without slipping, acceleration is R alpha and your friction force is less than mu s n.
What about B?
B? No, because I don't have
It's
my
not
yo-yo.
slipping.
No, we're supposed to teach your class without a yo-yo, right? Is that rolling without slipping? Well, it's not slipping. What's the friction force? What's the friction force? What's the friction force? 0. Right? We don't have any horizontal force. If we had a horizontal force, we'd be moving. So the maximum the friction can be is mu s n. But it's somewhere less, so it's usually less than this. If we're sliding, then the friction force is mu k n. And A is not equal to R alpha. So either A is equal to R alpha, or the friction force is equal to mu k n. One of the two.
So we have mu Kn once we slip in.
Once we start slipping, then we have mu k n. So what you need to do is figure, usually what you have to do is figure out what the friction force, you assume you're not slipping, and then you figure out what the friction force is, and if it's greater than mu s n, then you need to go back and resolve your problem a second time. Which is a little easier. So rigid body, general plane motion, sum of the moments of the external forces on a body about any point P is equal to what?
So it's not.
All right. Yes.
You guys all choke.
2, 1.
You good? Dang it.
What? Choke.
I won! Oh no.
E.
You got last.
So it's always the I about G, and then we can always do R cross MA. So this is the moment that the MA makes with respect to P.
Press the wrong button.
It's not the acceleration of point P, it's the acceleration of point of the center of gravity is how we deal with it. So as we're accelerating forward, basically the front roller is powered. So I'll come back to general plane motions. Are we powered or not powered? We are not powered. So the front roller is not powered. The rear wheels are powered because there's a motor. And so basically we're going to get a reaction force, a friction force, an XY force, and then we're going to have a weight that's going to appear on this. And then this is equal to mass times AG and IG alpha. And then we can take the moments about our point down here to eliminate the forces, and then we would have the R cross MA extra thing in our equations. Here we're pushing on our lawn compactor, lawn roller, so we can basically figure out what the acceleration is and the angular acceleration. And that depends on kinetic friction. If this is on ice and this is just going to slide, and then the wheel won't actually rotate. Here we have an impact. We have an acceleration of your belly button, your waist, which is attached to the seat belt, of minus 50 feet. Wait. It should be feet per second squared. So basically, we're going to have an acceleration here. What's the acceleration of the center of gravity? It's the acceleration of A plus the acceleration of G with respect to A. So we can do the sum of the forces where we're going to have a pin force here. And so what's going to happen to our per person? Who's going to hit the steering wheel? Which is why we want what? A shoulder belt, so then we have we can actually apply a moment about our person. Amazing. Engineers figured that out. So rigid body, acceleration, translation, and if we do both translation and rotation, which we've done both parts so far, is general plane motion. So we basically have the sum of the forces x equals max, sum of the forces y equals may, and the sum of the motions with g is equal to ig alpha. This is always true. And then sometimes we have additional constraints. We want to take the moment about point P, then what do we need to do? These two are the same. Moments kinetic, what is that? What's the I alpha plus whatever moments each of these accelerations are going to make about point P. So you have to include those. What's the advantage of taking the moment about point P? So if you have unknown forces acting at point P, then they're no longer part of the problem. It's a powerful sum of the moments you had in statics to get rid of several of your unknowns as well. Here we have a disk that's rolling without sliding. Those are your equations of motion, some of the force y, and some of the moments about g is equal to I alpha. So how many unknowns do we have in this equation? This is a quicker question. We have 1, 2, 3, 4, or 5 unknowns in these three equations. We know P. We're trying to figure out what's going to happen when we apply a force P on the center of our yo-yo. Oh, we can All right, we should be able to count to 5 within a minute. So it's 5 more seconds. 5, 4, 3, 2, 1, 0. Symmetry equation, you also have to have what? What don't you know? You don't know n, you don't know f. You don't know the acceleration of the center of gravity, and you don't know alpha. That's 4. Because you don't. From this equation, you can solve that it's equal to mg. But you can't use this equation to solve for it and then also know it at the same time.
Oh.
So you have 4 unknowns. We have 4 unknowns, which means what? We need another equation or we're out of luck. I think we just get another equation. So at least 2 people figured out. Actually counted. Oh, guess well. Right. So 4 unknowns in these equations. So we need another equation. 4th equation is either slip or no slip. If we are not slipping, then so you assume that you're not slipping. You calculate AG is equal to R alpha. It's your 4th equation. Don't use the friction force is equal to mu Sn. The friction force can be up to this, but it doesn't have to be this. Once you assume that, right, so here we have it. If we pull on it gently, calculate the acceleration. What happens if we pull on it really hard? Oh. We need the high-speed camera, but it's slipping. So if you pull on it gently, it's going to roll without slipping. If you pull on it too hard, it starts slipping. And so you assume, you calculate your friction force and see if it's going to slip or not slip. And then once you know it's slipping, then you basically have the friction force is equal to mu Kn. There's your 3rd equation, and then you're good to go. But Ag is not equal to R alpha if we slip. So, establish an inertial coordinate system, draw the free body diagram and the kinetic diagram. Assume a direction of the acceleration and alpha, and basically go from there. Some of the moments, T is equal to kinetic moments about P. Basically, you can do that to eliminate some of your ground reaction forces, and then you have your 3 equations of motion. Figure out your unknowns. Typically, we're going to have AG is equal to R alpha to start our assumption. Kinematic equations if we have more complicated linkage or something like that. If you assume no slip and you have time, like on your homework, you need to check the validity. On a test, you may not have time to do that. And I will tell you, you don't need to do that if you don't need to do that. Assume your direction, be consistent in your assumed directions. AG needs to be consistent with alpha. And then the friction force needs to oppose motion, which relates to the fact if you have a motor on your wheel, it reverses the direction of your friction force. All right. So here we have what? A spool which means mass 20 kilogram, radius of gyration of 0.3 meters. Coefficient of kinetic friction between the spool and the ground is 0.1. We want to figure out what alpha of the spool is and the tension in the cable. So, how do we go about doing this? Well, we want to focus on the spool. So, what's the magnitude of the acceleration of the center of gravity? .4 alpha, 0.6 alpha, 1 alpha, 1.2 alpha. acceleration is equal to r alpha. What's r?
Like 6.
R is the distance between what and what?
That's
The point that has no tangential acceleration and the center of gravity. What point doesn't have any tangential acceleration?
the ground.
Not the ground. What? Because we're given mu k is equal to 0.1. The rope isn't getting any longer. And so the rope is attached right here, and so R is 0.4. Right, it's tricky, because as you apply your moment, what's going to happen is that the bottom is going to slide this way. Right? Here we have, what happened? I pushed a button. So the answer was,
The thought that have mu k means that when we're sleeping.
yeah. If this is not slipping and this is not slipping, we're not moving.
Good point.
That's never exciting. That's a statics problem, and you can.
It's so
do that.
exciting.
It's not slipping, it wasn't moving, it's just rotating and it's slipping on the ground. That's what that thing's doing?
So what's this? As we apply a moment, what's going to happen?
We'll pull in, but it's
We're rolling, and so basically the string is winding up as you apply a moment, and the bottom is slipping on the ground.
Okay.
So now that we've done our little experiment, we can now try to figure out the solution to the problem. So what do we draw? First step is free body diagram and kinetic diagram. So what are our forces? There's so many red things before. We had it right earlier. I believe we had it right earlier. I put it right there. There's no friction. There we go. All right, what are our forces acting on our body? Gravity. So we have mg. We have N. We have a rope, and so we have tension. Anything else going on? Friction. Which way is friction going?
To the left. To the. Moving to the right.
As we apply our moment like this point we know has zero velocity. So as we're doing this, basically the bottom is going to be sliding to the right, so the friction is going to the left. And this is what? Mu k n. And we know it's mu k n because we know we're going to be sliding. So far so good? What's this equal to? We're going to have mass times acceleration, and we're also going to have I alpha. If the center of gravity moves, you're going to have an I alpha, and an MA, and if it rotates, you're going to have an I alpha. So far, so good. So our basic equations, we have the sum of the force x equals max, the sum of the forces y equals may, and the sum of the moments about p is equal to the sum of the moments kinetic about p. Those are our three basic equations which we can deal with. Where is a good place for p? What are our unknowns? We don't know n, we don't know t, we don't know alpha and a. So those are unknowns, and we can relate a and alpha by a is equal to 0.4 alpha. So we can solve for the normal force fairly easy, right? Sum of the forces y is equal to may. Sum of the forces y is equal to mg minus n. assuming positive is up, that's equal to 0. Because the center of gravity doesn't go up or down. So therefore, n is equal to mg. So now we know n. Happy. So we want to put point P at T to eliminate the other unknown in our situation. So what are some of the moments about P? Oops, we forgot something. How is this going to rotate? And we have a moment. Right? It's this moment that causes us to rotate. If we didn't have this moment here, we would just sit there and then it would be a static problem again. When t was equal to 0. Okay, so yeah, that's what we want. We want a static problem. All right. We could assume that, but then we would be wrong. Okay, so moments about P is equal to what? M minus mu k n times 0.6 plus 0.4 meters. So that's your moment. And that's equal to what? Well, it's mass times your acceleration times what? Times 0.4 meters. Is that going to be a positive moment or a negative moment? That's positive because, again, here is point P. Is that it? And then no matter where we are, we're going to have plus I times alpha. And so now we know what n is, we know what m is. And so m, what is m? So m is, so we're going to have 450 Newton meters, hopefully, yes. Minus mu, which is 0.1, times what? Times 200 kg times, what did I use? Hopefully I used 10. Yeah, 10 meters per second squared, just to make life a little bit easier. Times 1 meter, that makes life also easier. That's equal to, well, what is alpha? Alpha is alpha. What's A going to be? A is 0.4 alpha. So it's mass times 0.4 times alpha times 0.4. So that's equal to, our mass is 200 kg times 0.4 meters squared plus, what do we do for I? How do we figure out what I is? I. Well, what are we given? We're given the mass and we're given radius of gyration. And so I is equal to 200 kg times the radius of gyration squared. So this is mk squared. So if we do it this way, then we can figure out that alpha is 5 radians per second. And then how do we figure out what tension is? So we use basically the sum of the forces x. So from the sum of the forces x equals max, sum of the forces x is equal to what? T minus mu kn. That's equal to ma So we get t minus 0.1 times 200 times 10 meters per second squared is equal to our mass, which is 200 kg, times 0.4 meters times 5 radians per second squared. Yeah.
Could you just say real quick what you did right there at the bottom?
This?
No,
This?
stop.
A is 0.4 alpha.
So plus wait, but can you do that? It's plus that yeah, so it's that plus IA. Alpha, yeah.
I was just substituting this in for that. Is how we got
That's your,
up there.
is down here.
So it's mass times A is 0.4 alpha, times R, which is 0.4. That's how we get this mass times 0.4 squared. And then this is I, which is mk squared. And so then we have alpha. So we get AG equals 0.4 meters times alpha. So there's our tension, and from our tension is 600 newtons. Make sense? We could have taken the sum of the moments about the center of gravity.
We wouldn't be able to relate some of
Then we would have an unknown of t in it, and we still have two equations and two unknowns.
so it'll be longer.
That'll be longer. So by choosing point P to eliminate one of our, actually both of our unknowns. No, because we have this still. So by picking this to eliminate one of our unknowns, then we ended up with one equation and one unknown, rather than two equations and two unknowns. So your sum of the moments about P is equal. This is the most powerful equation you have, because you can wisely pick point P to get rid of some of your unknowns. If you're solving this by a computer, then it doesn't matter, because you have three equations and three unknowns, and you invert the matrix. You set it up in a matrix, invert the matrix, it doesn't matter. But to visualize what's going to happen, then it's easier to do it by picking point. Picking point P, you can get a good conceptual idea of what's going to happen. There's our beautiful thing. All right, concept quiz. 80 kJ spool. Now we have a force that is known. What direction are things going? What direction should AG be, and what direction should the friction force be? Sorry, friction force is first, and then AG is second. What is not here is that moment. Now, as we're pulling on the string, right? We're pulling on the string, and that's what's causing the motion.
Because I mean, if it's that way.
Did everybody get it wrong as well? going to go. When you pull on it, we pulled on it, so which direction is the acceleration going to go? To the right. How do we know that? Well, we saw it, but how would we know? What's the happy key point that you need to look for? Not alpha. It's a point with no horizontal acceleration, which is this, because we're rolling without slipping, or maybe we're rolling with slipping. And so if A is equal to R alpha, then this is R is the distance from the point of the ground to the center of gravity. And so that's going to be going this, so then the AG is going to be going to the right, assuming we're not slipping. What about friction force?
No. Because it's going this way.
So this is an interesting question.
I'm going to school.
It actually depends. Depends on the ratio of this ratio, right? Because as you're pulling on this, what's going to happen? It's going to want, the force is going to want your G to move like this. But what else is happening? You're applying a moment about G. If you apply the moment about G, it's going to want point A to go like that. So depending on what this radius is, the friction force might go.
So when with the radius of that, so the friction goes push to the right.
And so the radius of that, the book says that this is the right answer.
Yeah. Because once you create the moment at that point on the top, so we're gonna try to go in the other direction.
So the question is, yeah, we just looking at it, you can't tell.
But I was wondering, once the first 30 units, are we gonna go clockwise?
With some calculation, you can tell.
Yeah, but you can't tell the.
But you can't tell by just looking at it, because why? When you apply a force, you're going to have the total motion is a superposition of translation, that is ma, which is 30 newtons over m, and I alpha, which is just spinning around like this.
Yeah.
So the question, the I alpha wants the bottom to go like this, but so the bottom, with the moment, wants you to go like this. The velocity of the bottom is like this when you pull on it, but if it's translating, then the velocity is going the other way.
So it depends on the magnitude of the force.
Depends on the ratio of the 2 meters to the 0.75 meters. But I'm not going to penalize you. I mean, we can do the calculations, but again, you just assume it's going to go one way. And then what do we do? How do we solve this problem? So you basically solve it about, you take the sum of the moments about point A, which eliminates your friction force. And then once you figure out what the acceleration is, then you can figure out what direction the reaction forces are. So we know that G is going to the right, but going to the left or right, we're not sure. I would have guessed right. The book, I would have guessed left, right. The book says it's right, which is probably the right answer. But what's going on? Oh, I'm in a different world. What's the sum of the moments about G equation? Oh, then we have, let's just skip that. Let's not take sum of the moments about G. Let's do a different problem.
Oh wait, we're not.
So that's a hard problem that it's hard to figure out in your head. So, how are we doing in time? 3 to 7 minutes. Do this and do a couple things. So, I'll just do this problem. All right, so first thing we do is free body diagram. So we have 0 is equal to 0. Right, this is our free body diagram, and this is our kinetic diagram. We have a radius of gyration, which tells us what I is, and it's pushed forward with a force of 200 newtons. So we have 200 newtons at an angle of 45 degrees. What other forces are acting on us?
Gravity.
Gravity.
Moment.
Mg and
Friction.
friction. What direction is friction going?
To the right. To the left.
I don't know. Let's see, as you push it, you're pushing it from the center, which means if this was no
moment.
It's moving, the wind's
No
gonna move
movement.
to the left.
Bless you. As you're pushing it forward, it's going to want to rotate around like this. If we're rotating without slipping, so therefore mu(n) has to be like this to give you the moment to cause it to roll. What?
Is it the opposite of what you just explained?
But the last time, here the moment is going through the center of gravity. So this force doesn't have a moment about the center of gravity. Before, the moment was above the center of gravity. So we had both a force and a moment. This force is through the center of gravity, and so this force is not going to cause this to spin. It's only the friction force which is going to want to cause this to rotate. So before, this force was not at the center, and so the force causes this to spin and translate. This force only causes us to translate, and it's a friction force which is going to cause this to rotate. That's the difference here. But in reality, we'll take our moments about the base, and so it doesn't, if we're wrong, we're wrong. We can recover. All right. And this is equal to what? MA to what direction? Mass times A, and if we're rotating, we're going to get an I alpha. And if we're assuming we're rotating without slipping, we have that A equals R alpha, and we only have one R, which is 0.2 meters times alpha. Okay, so our equations, we have sum of the forces X equals MAX, sum of the forces Y equals MAY, and the sum of the moments P equals the sum of the moments kinetic about P. So that's our powerful equation. Where do we want to pick point P? Oh, this is wrong.
What?
The horizontal force, if we're rolling without slipping, is not mu(n). It's just F. Right? We don't. If we're rolling without slipping, then we know that we just have some friction force, and the maximum this force can be is mu(s) times n. But as we saw with the pen on the table, it could be 0. And then I found my pen after some help. So where's our cool point we should pick? The ground. So right, we pick point P here. And the advantage of P is it gets rid of 2 of our unknowns. So what is the sum of the moments about P? It's a component of this. This is the only thing that's actually going to give us a moment. So it's 200 newtons times sine 45 degrees. We need the horizontal component because the distance is 0.2 meters.
It doesn't matter.
Sine or cosine, doesn't matter. Oh, sorry. The way I drew it, it should be cosine. And this is a positive moment. What's this equal to? Well, I alpha is the easy part because there's always an I alpha. And then we have the R cross MA plus R is 0.2 meters times mass times AG. Is this is positive. What about this? Is this positive or negative? This is also positive because, again, this is point P, and so this if this were a force, it would also cause you to rotate anti-clockwise.
What is that MK? Some of the moments that.
This is the kinetic moments.
Kinetic.
So we treat
so
MA
this
like a force,
Oh.
and what's the force from the MA? What's the moment from this MA? That's a so it's the moment's kinetic
So the
about P.
diagram.
Yeah, so we treat all of our things like forces to get this equation right here. And so now we can plug in, and we know AG is equal to 0.2 times alpha. Are we given a mu? Oh yeah, we do have mu s and mu k. So what do we end up with? This is going to be 200 times 0.2, so this is 40 square root of 2 over 2 is equal to I. What's I? M. So it's 80 kg times, it's mass times kg, which is 0.175 meters squared. So this is m kg squared plus mass, which is 80 kg times 0.2 squared. All of this is times alpha. So from here we can get that alpha is equal to 5.01 radians per second squared. Thank you. So this is mk squared plus m r squared. Okay, so we're halfway, we're a quarter of the way there. So the sum of the forces x equals max. What's the sum of the forces x?
Component of the force applied.
So it's F minus 200 square root of 2 over 2, sine or cosine of 45. That's equal to 80 kg times what? R alpha, so it's 0.2 meters times 5.01 radians per second squared. And this is negative, assuming that positive is to the right. And so from here we can get that our force equals 61.4 newtons. Sum of the forces y equals may. That's equal to what? Sum of the forces y is mg minus n, and that's equal to,
There's a component of the.
oh, foodly-doo. And so it's minus mg plus n minus 200 square root of 2 over 2. And that's equal to 0.
The question just asked for alpha or acceleration, right?
Yes.
Okay.
But we assumed what?
That it wasn't.
We're assuming
That we're
rolling without slipping.
No.
So we need to figure out how this compares to mu n times, because we're given a static friction and a dynamic friction. So if we would find, so this, from here we can get that our normal force, where's our normal force, is 941.4 newtons.
Then it should be
And so mu s times n is equal to 112.9 newtons, which means what? Are we happy or sad?
It's great.
Which is greater than F, which was equal to, where did F go?
So we're good.
61.4 Newton. So we're happy. Our assumption was correct. So we don't need to keep on going. And no, we're out of time. So FYI, C and C are the two answers here.
Oh, you gotta be kidding me. Rough. You get that on